For the last talk of the day, we're going to have Guilherme Vedana from IMPA. He's going to talk about a complete classification of Fourier summation formulas on the real line.
Thank you, Tainara, for the introduction. Good afternoon, everyone. I would like to thank the organizers for the opportunity to be here to present this talk, Felipe, Manuel, and Mateus. So I'm going to talk about a complete classification of Fourier summation formulas on the real line. And this is a joint work with my advisor, PhD advisor, Professor Felipe Gonçalves. So we want to characterize summation formulas of this form here. Here, μ is a fixed, strongly tempered measure on the real line. This is, it defines a tempered distribution. This function A here is a compactly supported function which is complex valued. And, the support of the function A is countable. And it satisfies a hypothesis that we call locally summable. And by this I mean that for any compact interval on the real line, if I sum the A of lambda n for the points lambda n in this interval, this series converges absolutely. And this is the definition for the Fourier transform that I'm using. So I'm asking that the Fourier transform of the function phi, the integral of this Fourier transform against the measure μ is the same as evaluating the function phi at the points lambda n, multiplying by this weight A of lambda n, and take this sum. And I'm going to ask for this identity to hold for any test function phi, which for us will be a C-infinity compactly supported function on the real line. This hypothesis here of locally summable is just to make this sum well-defined. And in other words, I'm asking that for the Fourier transform of the measure μ, in the sense of tempered distributions, when restricted to this class, to this set, is the same as the sum of the Dirac deltas at lambda n with the weights A of lambda n. And this pair, μ and A, is what we are going to call a Fourier summation pair, FS pair for short, and this is going to be the main character of this talk. The first example of an FS pair is given by the Poisson summation formula. If you sum a function phi over the integers, the same as summing its Fourier transform over the integers. A second example is given by the Radichenko-Vyazovsky interpolation formula over the square root of n's, which can be seen as a family of FS pairs. They built even Schwarz functions in such that for any even function f in the Schwarz class, you can recover it through this formula by just knowing the values of the function f and its Fourier transform f the points square root of n. If you put the minus sign by a symmetrization process, if you put a minus sign here, here, and here, and you add these two equations, you arrive at this formula here, which now holds for any Schwarz function, which contains our test functions. And this for each x is another example of an FS pair. And a third example, which was discovered by Dinan and improved by Meyer, is this function here, which is supported at plus or minus square root of n over 2. And the coefficients is given by this term here. This R3 of n is the sum of three squares function, which is the amount of ways, number of ways of writing n as a sum of three squares of integers. And this function chi is given by this formula, which introduces some oscillation in these coefficients. And the Fourier transform of this measure μ is minus I times itself. And if you put the pair μ with the Fourier transform is another example of a FS pair. And more generally, if you consider a crystalline measure, which is the case where your function μ and its Fourier transform, they are sum of Dirac deltas, and such that both the supports, they are locally finite, we call this measure μ a crystalline measure. And this pair, μ with the Fourier transform, is called a crystalline pair. And all crystalline measures, there are examples of FS pairs, but observe that the definition of FS pairs is more general than that, because, for instance, the support of this set lambda n can have some limit points, or it can even be dense in some interval or in the whole real line, for instance. And this measure μ is allowed, for instance, to have an absolutely continuous component with respect to Lebesgue measure, for instance. And an example of, so all the examples that I mentioned here, the 3 examples, they are crystalline measures, but an example of an FS pair which is not crystalline is given by the Zellberg trace formula, which I didn't write here because it involves some technical terms that I prefer to avoid. And just to mention some connections with physics, crystalline measures and FS pairs, they appear in the field of crystallography, related to the atomic reconstruction of materials called crystals and quasi-crystals. I'd like to mention a few words about some recent results in the area regarding the classification of the structure of crystalline pairs. And the first recent breakthrough was given by Lev and Olevsky in 2015. And they proved that if μ is a crystalline measure, such that both the supports of the measure μ and its Fourier transform, they are uniformly discrete. This means that the points cannot get arbitrarily close. So they proved that in this case, your measure μ is supported in a very nice set. It's supported in it supports kind of a periodic set in the sense that it's given by a finite number of translations, a union of a finite number of translations of some dilation of the integers. Here, this theta j are going to be doing the translation, and this is the alpha z is the dilation of the integers. And you have a direct delta to lambda, and the coefficient that's multiplying is given by a trigonometric polynomial evaluated at the point lambda. And also Kurazov and Sarnak in 2020, they proved the following, that if you have P, a trigonometric polynomial with real frequencies theta n, which only has real zeros. And for the zero gamma, write m of gamma to be its multiplicity, which is a non-negative integer. And then you consider this measure here. It's given by the sum of direct deltas, supported at the zeros of your polynomial, with the coefficient given by the multiplicity of this zero. And so they proved that this measure μ is a crystalline measure. This is actually, the result is not stated in this way. This is a restatement using a result about Lie polynomials from Alon, Cohen, Vincent from 2024. And okay, observe that this measure here is this integer, non-negative integer valued. And in some sense, Olevsky and Malinowski in 2020, they gave a converse of this result, namely that if μ is a crystalline measure, which is n-valued, so there exists a trigonometric polynomial P with only real zeros, such that your measure μ, it must come from this construction here. And so this is a converse for the Kurazov and Sarnak result. And so there are several other results in the field. Just to mention a few of them, there are results from Meyer, Radichenko and Vyazovska, Ramos and Souza, Modarenko, Radichenko and Saip, Kulikov, Nazarov and Sodin, Alon, Vincent, and several others. Now let's move to our classification result. So it can essentially be read as follows. Given an FS pair, you can associate to it a unique holomorphic function in the upper half plane, C plus denotes the upper half plane, which is at the same time belongs to these classes, the almost periodic class in the upper half plane, and this is a higher order Nevalina class. And this function f is going to encapsulate the summation property of your pair. And you can know, starting from your pair, you can build this function explicitly. And you can go the other way around. If you are given a function f with these properties, you can build explicitly an FS pair μ and a. So this is telling you that any FS pair must confront a function like this with these properties here. Before stating the result with all the details, I'd like to introduce briefly each one of these classes here. The almost periodic functions, the intuition here is the following. Periodic functions in the real line, they under certain conditions, they can be represented by a Fourier series. So the intuition here is that we want to keep this property here and try to weaken the periodicity assumption the most as we can. And we arrive at this definition, which is due to Bohr, the mathematician. A continuous function f defined on the real line is almost periodic if, for any epsilon positive, there exists a set of translations tau in the subset of the real line, which is what we call relatively dense. And by this I mean that there exists some L positive, such that any interval of size at least L must contain some point of tau. And I'm asking that for any translation tau in this t in this set tau, this difference f of x plus t minus f of x, the absolute value of this, the supremum over all x reals is at most epsilon. And with this definition, you can define an analogous of a Fourier coefficient for your function f. You are going to take for lambda real, we are going to integrate your function against this exponential. Since now we don't have any more a period, you are going to integrate, you are going to take the average and send this t to infinity. And this is going to define you this Fourier coefficient. It's well defined. And moreover, you can define the spectrum of f to be the real frequencies such that the Fourier coefficient is not zero, which is always countable. And under certain conditions, you can have some Fourier, kind of Fourier inversion. Namely, if, for instance, this series here converges absolutely, and by this series I mean that I'm taking an enumeration of this countable set, and I'm going to take this sum over only the frequencies lambda for which belongs to this set, which is countable, and therefore this sum is well defined. So under this assumption here, you can recover your function f as a Fourier series, which converges absolutely and uniformly. Here, the main difference from the usual theory of Fourier series is that you are allowing any frequency lambda to consider for the Fourier series. And for the upper half plane, you can define an analogous notion of almost periodicity. So a holomorphic map in the upper half plane will be called almost periodic if now I give you some finite strip in the upper half plane given by alpha and beta. And I give you an epsilon positive, then there exists a set of translations tau such that for any translation t in your set tau, you are going to evaluate this difference and take the supremum, but now not anymore on a line, but over all points in this finite strip defined by alpha and beta that I wrote in the this region here. And you are asking for this supremum to be at most epsilon. And again, in this case, you can define a Fourier coefficient for a function f. It's given by an analogous construction. Now we are going to integrate over any horizontal line on the upper half plane. And you can prove that the limit, the result, does not depend on the horizontal line that you are taking. And again, the spectrum of f will be a countable set. Now, this is everything that for this is not about periodic functions. We can move for the Nevalina class. The classical Nevalina class, which we denote by N0, is a set of holomorphic maps in the upper half plane, such that the real part of f is non-negative. And if you have a function satisfying this property, it has what we call a Poisson representation, which says the following: that your function, there exists some non-negative measure mi, which integrates 1 over 1 plus c squared, such that and also there exist real numbers a and b, for which f can be written through this representation. So the integral of this kernel against this measure plus this I times this real polynomial. And conversely, any function f satisfying this property here, which can be written this way, belongs to this class N0. And you can ask what if I, instead of consider a measure with quadratic growth, if I allow a higher polynomial growth on my measure me. And by this I mean I need to put perhaps 1 over 1 plus c squared to some k. And this gives rise to the higher order Nevalina class, which is defined by the following. So the higher order Nevalina class of order at most k is an integer, is a set of all holomorphic maps in the upper half plane, such that for any choice of any points in the upper half plane, this Hermitian matrix here has at most k negative eigenvalues. And the important part here is the following. It doesn't matter how large n is, this matrix here will have at most k negative eigenvalues. And for the case k equals to 0, this definition is the same as asking for the real part of f being non-negative. And you have an analogous for Poisson representation. In this case, there will be, so given any function in this class, there exists some measure me, such that it integrates some polynomial 1 over 1 plus c squared to m plus 1 for some m at most k. And you are going to consider the integral of the sum kernel against this measure. But now the difference is that you are going to multiply by this polynomial, raise it to the m, and this q will be a real polynomial of degree at most 2m plus 1. And conversely, any function f which has this representation belongs to the Nevalina class of degree at most k. And we are going to consider the difference, this different set to account for the case where me is a signed measure. And so we can move to the main result. Our main result, it extends a previous result by Felipe Gonçalves from 2023. There he had the constraint that the measure me must have a quadratic growth at most. And we removed this constraint and allow any polynomial growth on the measure me, thus covering essentially all FS pairs in the real line. A simplification that we can do is that we can assume that the measure me is real valued, and we can assume some symmetry of the function a, namely that a of minus lambda is the same of a of lambda, but you need to put the bar. And given an FS pair, you can split it into two FS pairs satisfying these properties here, and then you can apply our classification result to each of these pairs, and so there is no loss of generality. And we are not allowing any growth on an arbitrary growth on A. We are going to, for A to have what we call a finite exponential growth, and by this I mean that this series here will converge for some alpha positive. And it turns out that this is not a strong hypothesis because essentially all the interesting cases of the FS pairs, they will satisfy this condition here. So we can move to the result. Let me and A be a FS pair, any FS pair on the real line, such that A has finite exponential growth. Since your measure me is, by definition, it's tempered, there exists some k for which this integral is finite. So fix this k integer. Then there exists a holomorphic map, f, which belongs at the same time to the Nevalina class, then is almost periodic. Not necessarily in the upper half plane, but maybe you need to translate it a little bit. And this c here of the translation is related to the exponential growth of your function a. And your function f has an explicit form. It's given by, it has this Nevalina factorization, and the important part here is the measure me appears in this place. And it has, since it's almost periodic, it has a Fourier series expansion, and now observe that the important part is that the coefficients, Fourier coefficients are given exactly by the function a. And you are taking into consideration just the a of lambda for lambda non-negative, and you are not losing information because we are assuming that symmetry property on your function a. And conversely, if you given f, a function f in the intersection of these two classes, you can go in the other direction and then construct explicit an FS pair me and a. Since your function is Nevalina, it has a Nevalina factorization, which looks like this. And for some measure mi and some polynomial q. And the measure mi can be, once you know f, you can compute this measure mi explicitly by what we call stilted inversion. And since your function f is at the same time also periodic, this Fourier coefficient is well defined. You can prove that it vanishes for lambda negative, and you define your function a to be this Fourier coefficient for lambda positive, and for lambda negative you just take the bar. And so this defines the measure mi and the function a. And to prove the summation property, you just need to apply a kind of integration, counter-integration argument, and you prove that indeed this is going to be an FS pair. And okay, and this finished the classification result proposed by Felipe Gonçalves, covering essentially all FS pairs under that conditions of finite exponential growth of the function a. And thank you very much.